Hello, Professor. This is my week 5 assignment. I'll now share my screen to explain my codes. For this first task, I located the dataset with heights, weights, and ages for at least 500 individuals. And what I have here, I read the first 5 rows of the data set and I did the visualization here. And with this, the weighted distribution for the males and the females are given here. And I also did box plot for it. And I have an outliner there. I removed the outliner with these codes and I did the plot over for the box plot as well as for the histogram. That is for before and after the outliners were there for males and for females. It's the same thing I did here for the box plot. This is before the outliners were removed for females and males, and this is after it was removed. And the test shows that the null hypothesis was rejected. There is a significant difference in the mean weight between males and females, and these are the statistics given there. Now for the next task, this is task 2. What I have here is the task to calculate the correlation coefficient between height and weight. This is the importing the libraries and the visuals. I did a scatter plot here, and the scatter plot shows a positive relationship here. And the value that I got was 0.46, and that is positive because the range is supposed to be from -1 to +1. And this means that 21.4%, that's when this is squared, this value is squared, of the variability of one variable can be explained by the variability of the other variable. So that is for task 2. For task 3, what I have is the linear regression model to predict weight based on height. And the 5 assumptions are here. And for the linear assumption, this is my code that I have here. And I fitted the line of regression on it too. And these are the points. And it was shown here that it needed to be transformed. When I transformed, I got this new graph here, but the issue was still not resolved, so I use a polynomial regression. With the polynomial regression, this is the new graph that I got. I also tried the logarithmic transformation, and this is what I got with the logarithmic and polynomial regression. I got these values here. For assumption 2, I use the QQ plot, and this is the plot here, and it shows that it follows closely to the reference line. For assumption 3, which is a multicollinearity, these are the codes that I have here, and the VIF value for height was 1.27, where 1 indicates no multicollinearity. But in this case, there's only one independent variable, and one independent variable multicollinearity is not a concern. For assumption 4, I use the For autocorrelation, I use the Dublin-Watson test. These are the codes here. And with the first run, I got 0.22. And it should be in a range of 0 to 4. It was closer to 0. And to resolve the issue, I use log variables here. And the value of the Durbin-Watson became 2.115. And to improve it even further, it shows a autocorrelation had been, oh no, in this case, sorry, it shows that the autocorrelation has been effectively addressed because it falls between the value of 2.115 and it should be around 2, indicating no autocorrelation. So with this transformation, it resolved that issue. For assumption 5, homoscedasticity, I did these codes here and I used the Brush-Pagan method. I have a value of 1.06. And to address that issue, I use log transform here, followed by winsorizing the data. I also did another transformation here. This is the other transformation. And the value was 0.93 now. And this is the linear regression for males and females shown here. I also built the regression model and for males and females with the equation. That is for task 3. For task 4, I use the data set from task 3 to build a multiple regression to predict weight based on height and age. These are my codes here. And I did the assumption test for linearity. This is the graph that I got. And it's roughly along the horizontal line, suggesting that linearity is reasonable. And I consider the lag term to address this issue. And when I replotted, I got this graph here. For the independence of errors, this is my plot here. I did a residual plot here, and it shows not much here. And for homoscedasticity, this is my plot, and it's fairly constant. For normality of residuals, I did the QQ plot. It followed the line closely. For no perfect multicollinearity, I use the VIF here, and the printout gave 1.00 for height, 1.00 for age here. And it shows that the assumption has no perfect multicollinearity. For no autocorrelation, I use the Durbin-Watson test. These are my codes here. And I got a value of 0.279. To improve on that, I include a time lag. And the value became 0.542. And I included more time lag here, and the values went down again to it went up, sorry, to 1.642. And the coefficient standard and other surveys are also provided here. And it also shows that there was an improvement in the R value. For the assumption of heteroscedasticity that I have here, I did the plot and I used the Brush-Pagan method and I got 139. Here I did a transformation of using the Cox method. And this is the graph that I got after I used that, and it became 103. To further improve it, I used the weighted least square method. And I got 101 now for the Brush-Pagan method. I used logarithmic transformation, and the value I got now is 88. I Winsorized the data, and the value became 86. Then I did truncation. And with truncation, the value is 69 now. Then I built the model. With weight, and this is the equation, with all the weighted value as well as the height and the age. But that is for task 4. Now for task 5, I did a statistical modeling for task 5, where I discussed 2 common linear regression models. I discussed linearity and homoscedasticity, and I did the regression model, one that violates the assumption. The one that I used was linearity here, and this is the plot that I got. And the solution that I propose, I use this data here. I use the original, and when I did transformation, and I also did polynomial model. And these are the printouts here and the plots. This is for the original, the transformed, and the polynomial. So that is for task 5. And for task 6, I use the data set from task 5 to propose a nonlinear model to predict the response variable. What I have here is the polynomial regression model was with a slightly lower MAE, indicating that on average, it makes smaller absolute error compared to the linear model. The adjusted R-square for the polynomial linear regression has a higher adjusted R-square value that might be a better fit for the data considering the degree of freedom. This is the graph that I have here. Yeah, and what I have here is the linear regression model and the polynomial regression model. And these are the various values that I got. And I also use some additional matrix, like the MAE, the RMSE, and adjusted R-square. These are the programs to those. And these are the printout for the values of that and the visuals. Okay, so this shows here that based on the polynomial regression model with a degree of 2 appears to transform slightly better than the linear regression model for capturing the nonlinear relationship of the data. So that's my presentation, and thank you.